That's a little region in Cartesian where your x's are trapped between two constants and your y's are trapped between two constants, right? Over here, it would look like this. Okay, so here, in this little region, your thetas are between two constants, and your radii, right, the two radii you have are between two constants. So this is a Cartesian rectangle, and this is a polar rectangle. A polar rectangle is not your standard rectangle. Like, you don't show this to like a third grader and be like, is that a rectangle? Because they're going to tell you no, right? But it's a polar rectangle, not a Cartesian. Understand this? Okay. So it's pretty interesting stuff, and you can actually go online and you can just Google polar graph paper and you can print this stuff out. And what's cool about polar graph paper is if you wanted to do like, let's say 7 pi over 6, like that. You want to graph that point polar. That means you're going to rotate by 7 pi over 6. So remember, this was pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, right? So I'm aiming this way, and I'm walking out how far? 4, 1, 2, 3, 4. So right there. See, I'm on one of those where they cross, kind of like you would be here on a point. How do y'all feel about this? Does it make sense or? Okay. We're not here to like see what we can do with this, but we want to at least appreciate it. So I'm going to show you one more example, and I think we can start talking final. This problem that I'm about to give you is a problem that was just a little piece of a problem from a test that I gave in a Calculus 3 class the other day. But it's something they had seen before, so I'm not saying you only see this if you take Cal 3. All right. I'll actually tell you what the problem was. I'll tell you what it was, and then I'll just focus on the part that you would have to do. So the problem in the Cal 3 was that we had a solid ball, a sphere, but solid. And this ball had a radius, I don't know, it was like radius 5. You could say 5 inches, 5 feet, 5 miles, who cares? And we could find the volume of this ball, right? There's a formula for it. We just look it up. Volume formula for a sphere is like 4/3 pi r cubed or something like that. So boom, we have the formula. But that's not what we wanted. What we wanted was, here's the North Pole, here's the South Pole. Imagine if I came in here with a drill bit, right? A drill, and I was going to drill out through the center of this ball. That would give you a different volume, right? If I drilled it out, it would take out that centerpiece. Yes? Okay. But that's not what I did. I drilled through, but let me draw my drill bit. This is going to be a very bad drill bit. Here's what my drill bit would look like. Okay, that's my drill bit coming through here, all right? If I drilled through the center, that's what it would look like, right? But that's not what I had them do, because that would have been too easy to find the volume. Instead, I offset the drill bit like this, so that the drill bit was just going to run down. This side of the drill bit would go down and touch the center line, but then the other part would just come through here. So if you drilled it out, it would have looked like this piece right here is drilled out off to the side. Understand that? And so they had to figure out what would the volume of that piece that remains be. And that's a pretty complicated problem, but one of the steps to the problem is they have to look at the shadow, or basically the projection of this drill and where it hits this middle portion, which would have corresponded to the XY axis, which would have been a circle down here, right? You would have had a circle down there. And what they had to do is come up with a polar equation that would draw that circle, right? That's exactly what I want us to do. But I'm going to now formulate the problem the way that you would see it, okay? Which would be this. This is a circle. The center of the circle is here, and then it goes through like that, touches there, right? What is the polar equation for that circle? What would draw that circle is the question, okay? R equals what? Okay, R equals 1 seems to make sense, doesn't it? But there's one problem with that. Remember, if I'm standing at the origin, right, and you say R equals 1, then that means I'm gonna go out 1, right, and then go around, basically. But the origin is here. So R equals 1 would draw me that circle, right? Yes? And you can't just say, all right, we'll just add 1 to move it to the right, because R and theta are no longer left and right, up and down. R and theta is how far you walk and turn, so you can't just simply add. You understand? Okay, so instead, here's what we're going to do. Do you know the Cartesian equation of that circle? Ooh. So you remember this formula? If you're going to do more math, I definitely think you need to make note of that formula. That is the equation of a circle that is centered at HK. Now, whenever we want to have a circle in the middle, h is 0 and k is 0, right? And then it just becomes x squared plus y squared equals r squared. That's the one most people are comfortable with. But as soon as we move that circle up or down, people start to lose sight of what the equation is. So what is the center of this blue circle? What is that center point? 1, 0, right? So let's refill this formula out, replacing h with 1 and k with 0. So this is h and this is k. So you get x minus 1 squared plus y squared equals r squared. But in this case, do we know what r is? What's the radius of this circle? 1. So this is 1. 1 squared is 1. Right? Do you all agree that this is the equation of that circle now? Okay, good. How do we go and convert this into polar? So remember, when it was just x squared plus y squared, we just switched the x squared plus y squared to r squared, didn't we? This time we don't have that. We have x minus 1. So we have really no choice but to do this. We're going to expand this whole thing out. So let's expand the left-hand side. Let's expand this. What's x minus 1 times x minus 1? We FOIL it out. X squared minus 2x plus 1, right? Plus y squared equals 1. Yes? Okay. Let's clean this up a little bit. There's 1's on both sides, so let's subtract 1 on both sides. X squared minus 2x plus y squared equals 0, right? Ooh. Do you see that in there? You see that x squared plus y squared? When you go from Cartesian to polar, x squared plus y squared becomes r squared. So right now I've got r squared minus 2x equals 0. I'm starting to make some progress here. Finally, do you have a conversion that takes x over to something with our conversions? What was x? We wrote it down, we boxed it. It was r cosine theta, wasn't it? So this will turn into r squared minus 2r cosine theta equals 0, right? That's what that becomes. I could move it, but it's dangerous. Instead, what I'm going to do is I'm going to factor the r out. Okay, so here's where I am now. I'll leave that one there. Let's factor the r out. We get r, and then we have r minus 2 cosine theta equals 0. And now that, since I've factored, I can set each of these equal to 0, can't I? So one equation is r is 0. And the other equation is r minus 2 cosine theta equals 0. This one, I'm going to just box it for right now. But on this one, I'm going to move the cosine theta to the other, 2 cosine theta to the other side. And I'm going to box that. All right. What in the world did we just do? Okay. We try to convert this Cartesian equation of a circle that was offset over to a polar equation. When we did that, we wound up getting 2 different polar equations. Now let's just think about whether or not these do what we want them to do. Does this do what we want it to do? This says, hey, you're going to draw a circle with a radius 0. No. This is basically a what do you call it? Solution. Oh my gosh. Extraneous, thank you. Couldn't think of the word. The other one, though, see, we have here that r is some function of theta, don't we? Kind of like when we had that line, I think I wrote 4x plus 3y equals 12. Remember that earlier? And I solved this for y. And when I solved that for y, I had like negative 3/4 x plus 3. Remember that? And then you could say that y there is a function of x. You give me x, I will supply you with the y, right? What we've turned out to have here is where if somebody tells me the theta, I can tell them how far to walk out. Instead of the ones we've done before where the r is fixed or the theta is fixed, now the radius depends on the angle. Does this draw that circle? Let's see. Let's see if it does. Do you think it does or no? It better, right? Let's see if it'll draw that circle. So I'm going to do this old school style, okay? Old school. You give me a theta, I will give you the r. So somebody give me a theta to plug into that equation. Give me some good ones. 0? If I plug in 0, what is cosine of 0 times 2? 2. Okay? So 2, like that. Right? Okay? Give me another theta. Let's go a little smaller than pi over 2. Pi over 4? Okay? So what would happen at pi over 4? We'd have 2 cosine of pi over 4. Right? Which is 2 times, cosine of pi over 4 is root 2 over 2, isn't it? And that would just be root 2. Yeah? Now give me pi over 2. So 2 cosine of pi over 2, what's cosine of pi over 2? It's going to be 0, so this is just 0. So let's see what we've done so far. The first point says that if theta is 0, I'm going to walk out 2. So if my angle is 0, I'm going to walk out 2. And it's going to draw that point right there. Okay? So far, I've got a point that's on the circle. If I change my angle to pi over 4, which is about right here, I'm going to walk out root 2 is 1.414 something. So I'm going to walk out that far, and guess where I'm going to be? Right there on that circle. Now, we didn't pick pi over 6, did we? But if you had picked pi over 6, that would be about right here. And you would actually walk out, I think, well, what is cosine of pi over 6? Cosine of pi over 6 is the x-coordinate at pi over 6, which is root 3 over 2. And then you would multiply it by 2. So you'd walk out root 3, which is bigger than root 2. So you would actually go out further. You would land right here. What happens at pi over 2? If I face straight up, how far do I walk out? 0. So I'm right here now, aren't I? So what I'm trying to get at is that if you take all the angles, right? If you take all the angles between 0 and pi over 2, you're actually going to draw this first part of this circle. Right there. And then what do you think it would take to draw the bottom half? You could do negatives, and you would draw the bottom half. Does this kind of make sense? So this equation is the polar representation of that circle. Pretty interesting. Something else that I'm going to put here. Theta between negative pi over 2 and pi over 2. So if I restrict my theta between negative pi over 2 and pi over 2, it will draw this whole circle, okay? I actually don't have to do it that way. I can go equals. So I'll give anyone in the class an A and they can leave for the rest of the day. No, I'm just kidding. An A in the class. No. But this is a pretty profound question. Is this circle a function? A function of x? No, because it failed the vertical line test. The reason why it failed to be a function of x was because back in Cartesian, if you pick an x value, there are two outputs, right? One up here and one up here. That's why we do the vertical line test. So it fails to be a function of x. Is this a function of theta, though? It is a function of theta. Because if I asked you to graph this, cosine, right? 2 cosine would look like, well, no, I totally screwed that up. That's a sine function. But this is a function, isn't it? Passes vertical line test. In other words, if I want to draw this point right here, right? This point down here, these don't come from the same two inputs for this function. They don't come from the same two inputs. But back with Cartesian, it came from the same input, didn't it? And therefore, we can treat this like a function. And that is very profound. Because once things fail to be functions, we kind of can't work with them in calculus. But once we can convert them to things that are functions, you can. So if you're ever like on some game show and they ask you, is a circle a function? Your answer is going to be, it depends, right? It depends. It's not a function of x in your standard Cartesian system. It's not. But there are other coordinate systems that if you can convert that circle into that coordinate system, you can work with them as functions. It's extremely useful. We do it all the time. This will take place in Calculus 2, where we can draw all sorts of crazy stuff. Like we can have a graph that starts to do like crazy things like this, and we will say that that is a function, even though it fails the standard, vertical line test. We're going to throw that vertical line test out the window. We're going to have another way of doing things, drawing things, which is good. And in Cal 2, we can actually take this curve off the sheet of paper and straighten it out and measure how long it is. It's called the arc length. But I get ahead of myself here. I'm sorry. All right, I think I'm done talking about polar. You'll see polar again normally in Calculus 2. That's where you'll see it again. And then it creeps out again in Cal 3. What time is it? 20 minutes? Did anybody not get the handout for the review? Okay. So I'm going to talk more about this next class, but I went through all the different sections for the entire semester, went through the homework assignments, and I picked out the problems that I thought were great. This is a good place for you to get ready for the final. I will narrow this down a little bit more, because right now this looks like a total massive cumulative final, doesn't it? Okay, so I will narrow it down a little bit more on Thursday. All I want to do on Thursday is go over problems. So what would be helpful for me is if you went and thumbed through all this stuff in your book and said, oh man, this one I don't get, and then that way when I come in on Thursday, I'm prepared to answer questions and address specific things that you need help on, as opposed to me just coming up here and being like, well, what do you want to see? Because I can't go through every single problem. There's no way. All right? This list here includes vectors, it includes polar coordinates, and it includes partial fraction decomposition. So pretty much everything that we've talked about is here. I'm trying to think if there's anything that we didn't put on here. The what? Yep, it's in there. Yep, dot product's in there. Yeah. Okay, I think I have like 20 minutes left. And I've done a very good job this semester of not filling your head with random useless information. I've been pretty good about that, haven't I? I mean, well, you could argue that all of this is random useless information, I guess, but I want to at least give you one thing, all right? And I promise on Thursday I'll do nothing but review. So I'm trying to think of one that might be interesting. I'll give you two to choose from. One of them is this. What does that equal? And then the other one has to do with what 1 plus 2 plus 3 plus all the way out to maybe like n equals. Okay, so these are two different sums. The first one I put up here is what we call an infinite sum. Like it never stops. You just keep doing this forever. 1, take away 1, add 1, take away 1, add 1, take away 1, add 1. All right, this one is you actually go 1 plus 2 plus 3 and you stop at n. Like what is that used to? So do y'all have a preference of what y'all like to see here?
I think we did that one.
We did that. Was that the one, the story with the kid?
Yeah.
Okay, so we've done that one. Okay, well that leaves this one then. What do y'all think this is?
0.
0 makes sense? Does 0 make sense? I mean, you're not going to get like counted off if you give me your opinion here, okay? So these are what we've referred to as series, right? Which you will study in Cal 2, Chapter 8. Series. This is what we call a finite series, and this is what we call an infinite series. This is a very interesting infinite series because it looks like it's 0, but then someone could argue that it also looks like it could be 1. It just kind of depends on how you want to look at it. Like if you just say, look, group these two together, what's that? 0, and then you can group the next two, and then group the next two, and then you basically are having like 0 plus 0 plus 0 forever. Yes? So yeah, it looks like it would be 0. But then another person could come in here and say, well, don't group it that way. Group it this way. So like these two together are 0, those are 0, those are 0, right? And so, right? You have 1 and then a bunch of nothings after that. So that would be 1. So maybe it's 0, maybe it's 1. It's kind of confusing, huh? A little bit? Okay, so let's try something. Let's try something. Let's just call this S. Can we call it S for some? Let's just call it S. Then do you agree that if I did this, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, so that's S. And then I take that S and I add to it another S. When I add those together, what should I get? 2 S's, right? But what would 2 S's be equal to? Well, I'd have to put another one of these, right? And add. So what if I did this though? 0 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. Is that still S?
Yeah.
I just put a 0 out front, didn't I? So if you add them straight down, term by term, 1 plus 1 would be, 1 plus 1. 1 plus 0 would be 1, and then you'd get
0, 0.
plus 0 plus 0 plus 0 plus, and you do that forever, wouldn't you? Which means that 2s would be equal to 1. Which means s would be a half. Ooh. The problem is you can't add forever, right? You cannot sit there and it's impossible for us to do this because you have to be able to go forever. It's an infinite sum. But does the answer make sense? Does that answer make sense? Like one person said it was 0, the other person said it's 1, and guess what it turned out to be? A half. It's like the middle, right? It's almost like the average of the two answers. So if I were to go out, and let's say I actually stop somewhere. So imagine this sum goes forever, right? I stop, you tell me when. Okay, right here. I'm either going to stop at a 1 or a -1, right? Depending on where I stop, if I add them up, I'm going to get one of two answers, right? I'm either going to get 0 or I'm going to get 1. Yes? Those are the only two answers I'm going to get. So this half is almost like giving you the average of what could happen if you stopped at some point. You either can get a 1 or a 0. 1 or a 0. So half is in between.
So, what if we take like one more s to like just see what happens?
What do you mean?
Like take one more s and put 0 plus 0, then start off the series again. Wouldn't that be the
Okay, so the question is, what if we did 3 s's, yes? So you want me to do s, 1 plus, 1 minus 1 plus 1 minus 1 plus 1, and then do another s, but you want me to offset it? Plus 1 minus 1 plus 1 minus 1, and then you want me to do a third s and just 0 here?
Or maybe 2 zeros or whatever.
Whatever you want.
I'll take 2.
You want 2 zeros? 2 zeros, and then what? Plus 1 minus 1 plus 1 minus 1. Okay, then add down. You get 3 s's equals, you're going to get what here? 1 plus 0 plus 1 plus minus 1 plus
There's plus 1 minus
1 minus 1 plus 1 minus 1, right? Like this. So here's what you could say, that 3s is equal to 1 plus 1 minus 1 plus 1 minus 1 plus 1 is equal to s, isn't it?
Mm-hmm.
So then subtract s, and you get 2s equals 1 again. Yeah, I know what you're trying to do, to see if you could arbitrarily make it be a different value. So what we're saying is that that's s, right? So you would have this algebraic statement. Good try, good try. So what about this? Look, I'm not trying to sell you on any ideas here. I'm just trying to show you that things get really kind of weird. All right? I'm going to see if I can remember how to do this. I haven't done this in a long time. Let me see. What do you think 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8 plus forever is? Are you trying it on your calculator? Yeah? See, you have to stop somewhere, right? And when you stop, as soon as you stop, you either get 1 or 0. You got -4? You may have typed it in wrong. You might have hit like minus twice or plus twice or something.
Let's try the same we did the one before that.
How do you mean?
Like equate that with some letter and then...
You want to equate that to some letter? Let's call this something other than S. How about we call it P, just for using a different letter? And then what do you want me to do? You want me to try and add P together with itself?
0 plus 1 and minus 2 plus 3.
Hold on. P again. Should we offset it? I think I've got that right. Okay, what would happen if we add these two together?
You get
2p equals,
You get 1 and then constantly -1.
you get 1
And you get 1
minus 1
minus
plus 1 minus 1 plus 1 Yes? But what is that?
That was S.
That's S. But what's S?
So P equals S.
What's S? 1/2. Hold on. This is 2P equals S, right? But S was a half. So 2P is a half, which means that P is a fourth. Okay. Now the last one, if you follow this, great. If not, I mean, this is just for fun. This last one should blow your frickin' mind, okay? Because those, I guess you can kind of see like, all right, you know, you add something, you take some away, add, take away, add, take away, add, take away, and at the end we're getting a number, right? Like 1/4. The other one was like an average between 1 and -1. This last one is just crazy. All right, last one. Let's call this, well, what do you want to call it? We've used S and P, F, okay. We're freaking crazy. All right. F is 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever and ever. Forever. Now, does it even make sense, or do you even think it's possible that this is a number? I give you $1, and then $2, then $3, then $4, then $5, then $6, and I do that forever and ever. Right? I do that forever. Can this actually be a finite number?
No.
Doesn't seem like it would be, huh? Doesn't seem like it would be.
Dragging out the suspense.
Yeah, I'm thinking I'm going to close this up until next class. I'm going to tell you what it is, though. That way you can go and think about it for a while. This is equal to -1/12. If you open up a quantum physics book right now, you must take this as truth. This should be disturbing. That you have positive numbers added up forever that sum to be a negative fraction. Isn't that troubling?
Sometimes we need to concentrate on exams. We can't concentrate on having that number at that point.
Yeah. That's kind of crazy, isn't that? I mean, yes, that has to be crazy to you. Right? I mean, that's like totally irrational. How can you possibly add up positive numbers forever and get a negative fraction? But a lot of our major concepts, physical concepts, follow that rule. What we have is what we see this summation in nature. We see it, and every experiment that we've done, if we replace that summation with this, we actually get the result that we expect. It's crazy. So, I got in trouble. One of my fellow faculty members came up to me a couple of semesters ago and was like, I heard that you told your Calculus 2 class that the sum of the integers is -1/12. It's like, yeah, I did. It's like, why'd you tell them that? I said, well, because they need to understand that math is kind of crazy at some point. It gets irrational. It gets kind of against what you think, and you know. Okay, so next class I will show you why that's true. Or at least that's what we accept to be true for certain summations. So Thursday, your test, your final is when? Thursday, right? Next Thursday. So on Thursday at 12:30, not at 1 o'clock. Yep, it's at 12:30, not 1 o'clock. All right. Hopefully you'll come in with questions on Thursday, -1/12.